So the first thing I want to mention is last class we did finish up M3. So those out-of-class exercises for M3, I'm going to have you finish those up and have them due for Friday of this week. So that'd be October 27th. And then from there, I'll figure out there's some other stuff on the calendar that's set to be due, like, N1, N2 and stuff like that. I'm going to have you ignore that stuff for right now because it looks like that stuff was already graded a long time ago. But we'll go back and figure that out here. Hopefully by Monday I'll have grades figured out. But for right now, that assignment is going to be due for this Friday. And today I am hoping to work on M4 and M5. And we will be grading out-of-class exercises for those. Will be due for next week, Tuesday. Which is going to be what, October 31st, it looks like. So Halloween day. And the only reason I'm setting them for Tuesday instead of for Monday is I want you guys to have, if there are questions that come up, you have a day on Monday, you can ask me questions in class, help get those finished up before they have to be due. And then it does look like he's been grading the preparing for the next lesson assignments. So PNL, that was for M4. It was at the end of M3 from last class, from Monday. I might ask you to work on that for today, so I'll have that due on Friday as well. Then hopefully from there we'll be able to get a better assignment schedule figured out for us. PLN or PNL 5 is probably going to come in there as well. That I'll probably make that due. Oops, M5. We'll have that be due next week, Tuesday as well, even though we'll try to cover that lesson today. So I'd asked you on Monday to take a look at that, preparing for the next lesson at the end of unit of M3 there for preparing for M4. And they talked about linear models. The first one was Zeke driving from his house to the beach and wanted to come up with an equation for that. When we come up with an equation, most of our equations have two parts in these types of models. We've been looking at linear models. So the first thing to determine is that a linear model? Well, we have to ask what is being modeled, first of all. So for that PNL for M4, number one, Zeke driving from his house to the beach. What are they asking you to model? Do they want the equation to describe his speed? Do they want the equation to describe distance from the beach? Distance from home? Distance from home. Okay, so that's the first thing. So the second thing we need to ask, back to that question, is it linear? Well, what would have to happen for it to be linear? Well, the only thing we're given here is a starting point, a starting distance, starting 50 miles from home. Will that affect whether it's linear or not? But what does it mean to be linear? Linear talks about how it changes. And more specifically, rate of change. Does it change the same amount for every chunk of time? Yeah, and what tells us that it's changing the same amount for every chunk of time? Perfect. Perfect. It's a constant speed. And the technical term for that is a rate of change. So it is a constant rate of change. So that tells us that is linear. So once we know it's linear, a linear model has two parts to it. The first part that the linear model has is a starting point. Sometimes referred to, I'm going to scroll up a little bit here, as an initial value. And then it has some sort of a, I'm going to put plus or minus here, rate of change, and then some sort of variable. I'm going to put x, x or t or whatever you would use for your variable, depending on what you're looking. In this case, we are talking about time, so it probably would be somewhat more appropriate to use t for our variable. And then that's representing some sort of a total. So in this model, the starting point was what? 50 miles from home. Now, the rate of change, notice I put plus or minus. Is the distance from home increasing or decreasing? It's increasing, so it's plus. And that rate is just the 65 miles per hour. And then that's going to be times our time, and that's going to equal total distance from home, which they're labeling with D. So there's our model. And you can see the way I wrote that out is I put it in words. Now I just did generic words here, but I could be more specific to the problem. The starting point, I could have wrote distance from home at the beginning plus speed times time. Some things we know about this model because of the unit here, the units of our speed is in miles per hour. So that tells us that time must be in hours. Perfect. So let's do number 2. Ezra has a base salary of $25,000 and 65% commission on vacuum cleaners. This means that each vacuum cleaner he sells earns an additional amount that equals 65% of the price of the vacuum cleaner. So answer the following questions. Well, before we answer those questions, let's put a model together for Ezra's pay. So his pay is going to equal, is there a starting amount or a base amount? Well, let's just figure it all together. It's saying for his pay for the year. So his total pay for the year is what we're trying to represent here. So we'll keep that in a lump sum for right now. So is there a base amount that Ezra gets? Well, the key word here was base salary. Which was how much? 25,000. Good. And now he gets a commission. Is that commission going to increase or decrease his pay? Increase. So it's going to be a plus. And that's going to be a commission rate. What's that commission rate going to multiply by? That'll be 0.65. That's good. That's the 65%. And it's 65% of what? Of his sales, right? So we'll use the letter S. I always shy away from using S because it looks like my 5s when I write it. But we'll use the letter S to model that. And so there is the linear model for it. Now we can use that to answer some questions I'm going to go off now back to the assignment here. Part A says, how many dollars in sales to earn a total pay of $35,000? So the 35,000 has to represent one of our variables in this equation. Which variable does it represent? P, the total pay. So we would put that in there for the total pay. Oops. And then we've got to solve for S. How do we solve this for S? Perfect. Now we think of it as a balanced equation, and we've got to take it apart. So we subtract the 25,000. So what's left? $10,000 equals 0.65S. Good. And from there, we will divide by 0.65. Perfect. So we need to do the 10,000 divided by 0.65. So 15,384.62. Perfect. Now the next one is, if vacuums are sold at $200 each, how many does he need to sell? This is an example of where you can use your labels to do some calculation. It's something called dimensional analysis. And it's used if you're doing measurement conversions. You use the units to figure out whether you multiply or divide. What we're going to do is we're going to take his total commission or his total sales here, and we're going to convert that into number of vacuum cleaners. That's a dollar amount. That's the label on that. We're going to make it a fraction by putting it over 1. Now, the $200 each, what that is saying is $200 equals 1 vacuum cleaner. So I'm going to convert dollars into vacuums. I've put dollars on bottom, vacuum cleaner on top. 1 vacuum cleaner is $200. The reason the dollars had to go on bottom is so that the dollars as a unit cancel out. And what I have is a vacuum is my final unit. So this is 15,384.62 divided by 200. Comes out to 76.9, which of course we're probably going to have to put as 77 vacuums. All sorts of things could have happened to reduce that commission. There might have been expenses, or maybe had to sell some at a discount to get them to move them or whatever. So we have to round up. At least 77 vacuum cleaners. Could have been more. Okay. Any other questions that you guys had off that P&L that you want me to go over? Okay. So I'm going to leave that. We're going to start on our lesson here. So what we've been looking at here is linear models. We want to take a look now at other models that might still be linear, but may not be quite as clean. And the biggest thing is that starting point. If the starting point is not at 0, how do we come up with a model for it? So let's say that on my graph here, I know that a line has a point here at, let's call that 80 and 60. And it goes up, it has another point somewhere. Well, let's just say that it has a slope of 0.3. So that slope of 0.3 is telling us what? For every 1 unit it goes over, what is it? How far does it go up? 0.3, right? Another way of interpreting that is vertical change is equal to 0.3 times the horizontal change. So rather than going over just 1 unit, it's a little bit easier for me to conceptualize if we go over several. So let's go over 10 units. Let's go over to 90. If I go over to 90, I've gone over 10 units. How far do I expect this to go up? Well, is the 10 vertical or horizontal? That's horizontal, right? Side to side. So to get my vertical change, it's going to be 0.3 times the horizontal change. So 0.3 times 10 is 3. So I've got 3 horizontal change. So this point here was 80, 60. This point is 90, 63. From those 2 points, can we find where this would have come back here? Well, I could have actually used this formula and worked backwards if I wanted to. I know that the slope is 0.3. Once I know that, I could have, now I'm just going to call this x and y for simplicity right now. My y value equals some sort of starting point plus that slope times x. To figure out that starting point, I could plug in one of these initial points, 80, 60. The 60 would go in for y. The label I'm going to use for the starting point is just the letter B. And I'm going to put 80 in for x. So what is 0.3 times 80? $24. There you go. And then, so how do we find B from there? Subtract 24. Very good. So 36 equals B. So what that's telling us is that the model for this is y equals 36 is the starting point plus 0.3x. So what I want you to do is I want you to start reading problems in M4. I want you to read over problems 1, 2, and 3. And just take some time and look them over, read them over quick. I'm going to give you a few minutes. Think about how you would model those situations, and we'll talk about them here in just a few minutes. So the price for the usage of water here is, it's called a tiered system. Come on, there we go. And what that means is there's a cutoff below a certain volume, below 20,000 gallons. What's the price per gallon or per 1,000 gallons? $12.04 per 1,000. Yep. And then above 20,000 gallons, it is $21.90 per 1,000 gallons. So I just kind of set up a quick spreadsheet here. Our cutoff is 20,000 gallons. So for 15,000 gallons, It's just going to be that amount times 12.04, correct? So did you get $180.60? Okay, good catch. We've got to add the flat rate to that. So plus $73 exactly. Perfect. So 253.60. Perfect. Now the next one, we haven't gone over 20,000 gallons yet, so that's going to be the same formula. So 289.72. How about the next one? At 20,000 gallons, do we go to the next tier yet? 20,000 is our cutoff. So for the first 20,000. So the next gallon would be in the next tier. But so far, we're okay. We can stay right there. At 25,000, we're going to have to split this up. And this is going to be a little bit tricky to write a formula for. So we've got our $73 plus $12.04 times 20,000 plus 2190 times, what I'm going to do is, actually I can't have the 1,000 there, it's just in 20 at 20. And here I'm going to take this number minus 20,000 because the first 20,000 is already paid for in this little piece right here. So did you get 423.30? Okay. Let's talk about what we did here. So the 73 here, of course, is just that flat rate, the having the service fee or whatever they want to call it. Then we took $12.04 times 20. That was the rate for the first 20,000 gallons. Then we took $21.90 times the remainder. So that was A5 is just the amount over here minus 20,000 because we're only charging that higher amount for the amount over 20,000. Any questions on that model? Very good. I was waiting for somebody to mention that. We have 20,000 gallons right here. That $313.80 is what the first 20,000 gallons costs. So we could, and I'm just going to put it beside here and show that it comes out to be the same, take $313.80 and add to that what additional cost we have to do for the amount, because that is for 20,000 gallons from up here. So then we're going to add 2190 times, we would still have to do this amount minus 20 to show that it's only $21.90 for everything above 20,000 gallons. And you'll notice we get the same answer. So it's kind of like I had mentioned yesterday at the beginning of class. When we're dealing with these, there isn't just one correct way to do it. There's often several ways, and we'll see they all come up with the same answer if I do that formula. There are often several ways you could go about getting that solution. Hey Sam, how's it going? Good. We're just doing questions 1 through 3 on M4 here. No problem. So we've got that table figured out. Did you guys get time to plot them on a scatter plot? Okay, take about 2 minutes here quick and plot those on the scatter plot. So as you're plotting those points, you'll get dots on your chart similar to what I have here. And what you'll notice is if you wanted to connect them with a line, You would have one line here. Now, without even having to calculate it, what do you think this point would be right here on the axis? If we traced it all the way back. What's that starting point have to be? If they use 0 gallons, how much are they going to get charged? There you go. Very good. $73. So that's what that point means. That's what they're going to get charged if they don't use anything. That's the starting point. And then it goes up by that $12.04 a gallon up to 20,000 gallons. Or $12.04 per thousand, I should say, up to 20,000. But then what's going to happen to our line right here? It turns ever so slightly. There's a change in, there you go, in the rate. And the algebraic term we use for that is slope. Not stop, slope. There we go. There's a change in the rate of change, a change in the slope of that line. So we have to describe these two lines with different equations. So if we're going to describe that equation, this line from there to there, well, we have y equals the starting point of 73 plus, what's our rate of change at that point? 12.04 times, let's use G for gallons. We know that G is 1,000 gallons or a kilogallon, right? So that's the equation for that part, but that's only good from 0 to 20,000 gallons. So there has to be another formula that describes this for greater than 20. And so I went over this a little while ago. We know that it goes through that point there at 20, and what is the value that we had? Oops. If I can get my graph to move. Maybe not. Well, it went through 20 and we had the value of 313.8. There we go. So we know we go through that point. So I'm going to jump back to my Word document so this looks a little bit neater. So we go through that point. We know that that is 20 and 313.8. What is the rate of change as we continue from there? The per 1,000 gallon rate? Yeah. 21.9. So what that tells us is we have an equation. Well, let's just go to cost here, price, whatever. What variable did you guys use for the total price? Did you use P or C? It really doesn't matter. We'll go C for cost. That cost is going to equal some starting point, which we don't know yet, because that starting point down here is kind of imaginary because the line really doesn't go there. Some starting point plus, because it increases for every 1,000, that 2190 times our gallons consumed. Now we know that that's only if we're over 20,000 gallons, but we'll worry about that later. So to find this starting point, we have to use this known value. What does the 20 go in for? What does that represent? The cost or the number of gallons? $20 is the number of gallons, 20,000 gallons. So 20 is going to go in for that. And I'm going to use that capital B for our starting point again. The 313 then is the cost. So to solve this equation for that starting point of our equation, we have to combine what is 2190 times 20. You have 438. Is everybody any questions as to where that 438 comes from? That's what that 20,000 gallons would cost if we were charged at the higher rate. In other words, that's the slope that that line is going to have after we go past the 20,000 gallons. So now to find out what that starting point would be, we got to subtract the 438. So we've got 313.80 minus 438. Negative 124.2. So this is giving us our equation now. For that line, again, that's the line after this change of slope here. Oops. Let's get back to my control panel. There we go. After this change in slope, the equation of that line would be that the cost is equal to a negative $124.20 plus $21.90 per 1,000 gallons, where G is 1,000 gallons. Now we know this line isn't real because there's never going to be a point. This equation is telling us that there's a point where there's negative cost for the water, and that's not true. So what's the restriction on this equation here? It's only good when more than 20,000 gallons. So the concept that's being introduced here is a piecewise function. And what that means is there's a very distinct function for one range of the graph, and it changes to another distinct function for another range in the graph. That's exactly what we have here. For the first 20,000 gallons, we have a line that looks like that. And I'm going to exaggerate. After 20,000 gallons, the line looks like that. We have to, in order to describe this section of the line here, we do have to extend it so that we see where it intersects that y-axis, that starting point or initial value. But it doesn't mean anything. This section of the line doesn't really exist, but we have to find it in order to describe it. So the equation here, the cost for the water would be $73 plus $12.04 per 1,000 gallons if G is between 0 and 20. So between 0 and 20,000 gallons. After that, the equation becomes negative 124.20 plus 21.9 times G for G greater than 20. Now, one thing that we would have to double check, because this function, the lines do continue. It just stops here and it just turns. It doesn't make any jumps. We would want to make sure those two equations give us the same value at the point where they change at 20. So I'm going to have you double check that quick. If it's 20,000 gallons, do those two different pieces of that equation give us the same value? So I'm going to pause for a second and let you guys try that. Did they work out? Perfect. So then we know that works, that those two equations fit together. So now let's say we wanted to use this equation like we did some of the equations we had in the P&L section there, of use it for calculating how many gallons it would take to get to a certain price and whatever. So let's say that the cost is $280. And we want to know how many gallons were used. Well, any ideas on how we'd go about, how would we know which formula to use? Okay, perfect. You guys just checked to make sure that those gave you the same values when you put 20 in for G, right? And both of those, what was it, 313.80? Is that correct? Yeah, so when you put 20 in for G, both of them gave you 313.80. So since this cost is less than that, we know we have to use the top formula. Now, if we hadn't just used the top formula, or hadn't just done this double check, we could go back and put 20,000 in one of them and see what we get, and then compare. Or we could have just gone ahead and solved using that top formula. What's the first thing we got to do to try to solve this? Subtract 73, good. So 207 equals 12.04 G. And then divide by 12.04. So 207 divided by 12.04. So we get 17.193, we'll call it, equals the number of gallons. So that actually would be 17, that's in thousands of gallons. That'd be 17,193 gallons. Is that less than our point of where we change? Yes. It's less than the 20,000 point. So we know we're okay. Let's look at a price of $350 now. And I know you guys are looking at this and you realize we have to use the second formula. But I'm not making a mistake here. It's not a mistake to do it, but let's say I don't know that 313.80 is that cutoff. So I'm just going to throw that 350 into that first formula. See if you can beat me to it to solve this one. What'd you get? So 23.00? 0.01, okay. So G is 23.01. Now that came out to more than 20, which tells us we can't use that formula. Yes, we have to use the other formula. We have to use the negative 124.20. So I'll put the 350 in again. Negative 124.20 plus 2190 times G. Again, see if you can beat me. What'd you guys get? $21.65. So 21,000, about 650 gallons. Now, do you expect this number that we just got here to be bigger or smaller than the number we got up above? Well, let me let you off the hook. This 2301 is what we got up above. Why should this number be smaller than this one? This one was charging at a smaller rate. Both of them were equivalent. At 20, if we look at our graph, again, I'm going to exaggerate it. At 20 or 20,000 gallons, both formulas would give us the same price. This formula, however, as we went above that, kept going at the smaller slope, which means we'd take more gallons to get up to that same height. Whereas the other formula goes steeper, so it gets up to a higher price sooner, so it takes fewer gallons to get there. As you're doing these problems, that's one of the biggest things that you need to think about is why. Because if you understand why this number is smaller than that one, when you're working on these problems on your own, you can go through that thought process. Do I expect this answer to be smaller or larger than this previous answer? And by doing those little estimates and those little thoughts in your head, it helps you avoid some major mistakes. If I had done this calculation and got a number bigger than this, I would know that it's wrong. Okay, well, what I want you to do is I want you guys to take a couple minutes, read through problem situation 2, the cost of moving, and we'll start talking about that in just a couple minutes. Okay, so let's take a look here at what they have is 2 different options for moving. They have rent a truck and trucks for less. So we're going to talk about R is going to be rent a truck. So what do we know about rent a truck? What's the minimum cost for rent a truck? $40. And that $40 is good for how long? How many miles? So if we sketch a graph, it's $40 and it goes over a flat line to 40 miles. At that point, it starts to cost them more. How much does it cost them per mile? 60 cents per mile. So that means there's a slope here of 0.6 per mile. So I'm just going to make a big jump over to 80 miles here. So that's a difference of 40 miles. So that'd be 40 times that slope of 0.6. We expect it to go up by 24 miles. So at 80 here, we are now going to be at 64 here. Right there. So the blue line is our model for rent a truck. Tell me how to do the same thing now for trucks for less. Oops, I actually used the C in that one. Where do we start out with that one? $25. How long is that good for? 25 miles. So a flat line at $25 over to 25 miles. Then what rate does it go up at? So it's a slope of 0.8. So let's go over to 80 again. So how much did it change from 25 over to 80? What's the horizontal change? 80 minus 25. 55 miles. So the vertical change, remember, is the horizontal change times the slope of 0.8. So 55 times 0.8 is 44, right? So for that 55 miles, it went up 44. So it started at 25. Where's it going to be at over here? 44 plus 25 is 69. And we were at 64 before. So it's actually slightly more than the other one. So we know at 80 miles, the trucks for less is going to cost us more. Now, there are a couple of things we want to find here. One, we want to be able to represent each of these with a function. Let's look at the blue one here, the rent-a-truck first. Remember, we talked about that piecewise function. And the piecewise function changes when the slope changes, when we're talking about linear functions. So where does the slope change? What x value does the slope change at here? That's where the slope changes right there. That's at 40 miles, right? So for rent-a-truck, the cost for rent-a-truck, for that first 40 miles, what is the cost? Oops, that's just a flat line there, right? So it's just 40 bucks. If the miles are less than or equal to 40, that is just at $40. Now, after 40, it starts to slope up. So we've got to come up with a formula for the miles greater than 40. How do we come up with that formula again? Well, we've got to solve this equation. We have one point on that line right here. What's that point? 40, right? And after that point, the slope is? After that point, the slope is 0.6. Very good. So to find that equation, R is equal to 40 is the starting, well, we got to do this. B is the starting point plus 0.6 times the miles. We know that the cost was $40. When the miles was 40 miles, find B there. What'd you come up with? Okay. Oops, careful. You went backwards. So we've got to combine the 0.6 times 40, which is 24. There you go. So it's B plus 24. Then what do we have to do from there? Subtract 24. Wonderful. So the y-intercept is B is 16. Oops. So that means that formula is, come on, there we go, 16 plus 0.6 m. So there is our equation for the rent-a-truck. I want you guys to do the same thing now. I'm going to give you about 3 or 4 minutes. Do the same thing to find the equation for trucks for less. Here, I'm going to scroll down so you can see what I did for rent-a-truck. How did you describe the flat portion of the line? What value is that line at? It's at 25, yes. And it stays at a value of 25 up until what mileage? It's 25 miles. So for m less than or equal to 25, it's just 25. So now you have to find what the equation is that describes it when m is greater than 25. So you can see what we did over here, had the slope, had the starting point, and we solved to get what that y-intercept was. So if I'm going to set up in a generic equation here, trucks for less, the cost for trucks for less is going to equal, I need some starting point, which I don't know what it is, plus what's the slope of that line? 0.8, perfect. Times the miles. And we know that there is one point where we know the value of both t and m, and that is right here. For that point, the miles is how much? 25. So that's m. And what is the cost, t, at that point? Also 25. So what do I do to solve for b here? First step is going to have to be to combine, right? 0.8 times 25, which is? Okay. 20, perfect. Then what do we have to do to solve for b? It's b, subtract 20, there you go. So b equals 5. So what that's telling me is back up in this equation here, b is 5. I can replace b with 5. So this is 5 plus 0.8 m. That was how I found this one up here too, yes. So yeah, this is, okay. All equations, when they're linear models, remember, have the form that sum total is equal to a starting point time, or plus, I should say, plus or minus a rate of change, which is the slope, times some value, whether it's x or t. I'm going to change my multiplication to a dot instead of an x. So times my Some textbooks call it predictor variable, others call it independent, others just call it the X variable. In this case, that was the miles, but times my independent variable. And so what we did here was we knew the rate of change was 0.8. So we just put in, since we're talking about trucks for less here, we put in T for the total for trucks for less. That's saying the total cost for trucks for less. Our starting point, I just abbreviated that. The mathematical variable we use for abbreviating that is usually the letter B. Our rate of change was at 80 cents per mile, and it increased for every mile, so it was a positive 0.8. Then for the independent variable, we just put in the letter M because that was the number of miles. Now we have, this is most of our equation here. We just need to know what B is. To figure out what B is, we go back and we see if we can find a spot where we know the value for T and M. Remember, M is the miles and T is the total cost. And if I look back up here, there's one spot where we knew that. That was right here. Now the key is it has to be on the sloping part of the line, and that is. At that point, there was 25 miles and $25. So we put 25 in for miles, $25 in for T, and now all that was left was B. So then we solved that as we did up above to get 5 equals B. So that meant we could go back up to this equation and replace B with 5. So total cost is 5 plus 0.8 M. And again, that equation only applied when the miles were greater than 25. Because if the miles were less than or equal to 25, it was just a flat 25 bucks. You bet. So the next question. When we were working up above, when we did that piecewise function, we tested to see if it met at the same point. We tested to see by checking to see if we got the same value at that point. One of the things we could have done was just set those two equations equal to each other. Well, here, I want to know at what point is the cost of these two trucking services. In other words, how many miles to make them equal, to make the cost the same. Now, if basically what that is where those lines cross on the graph, is where that cost is the same. Do you have any ideas how we can find that point? Well, do we know how to describe the cost along this line here? That's the trucks for less. That was, yep. And then the cost along this line here was the rent-a-truck. Was that, right? If I want, okay, if I want this cost to equal that cost, that means this expression has to equal that expression, right? Now, the only restriction to this, before you start to solve that equation, what is the restriction on this? The mileage has to be larger than what amount? Well, it obviously has to be more than 25 because there's no way that they're ever going to equal if it's less than 25. But 40 here, if we don't go past 40 miles, well then this equation doesn't describe the rent-a-truck anymore. Does that make sense? This equation only applies after we reach 40 miles. Before 40 miles, it was just a flat $40 fee. So if we solve this and we get an answer less than 40, we've got problems. Hopefully we don't have an answer less than 40. So tell me, what's our first step to solving that? You have to combine like terms, but right now they're on opposite side of the equal sign. So how do we do that? Okay, so we want to deal with the variable first. It would be, yeah, which one do we want to get rid of? Go ahead, Sam. What are the variables we got to get rid of, right? Yes, so which one would we get rid of? The smaller one, very good. And we get rid of it, it's positive, so we get rid of it by subtracting it. So that would be gone, leaving us with 16. But remember, these equations are kind of like a balanced scale. If I take something off one side, that scale is going to tip unless I do what? Well, unless I do the exact same thing to the other side. There you go. So I got to take 0.6 m from this side. The only thing I can take it from is another m because they have to have that same name or like terms. So 0.8 minus 0.6 is 0.2 m. Now we know how to solve this. What do we do? Okay. And then divide by the 0.2. So 55 equals m. So the same cost at 55 miles. And it's more than 40, so we're okay. We know that it works. If it was less than 40, then we would have to go back, and instead of using this expression, we would have just put in 40 here, which would have been a lot easier to solve because it'd be just 40 equals. We wouldn't have a variable on both sides. Okay, any questions? So as I mentioned at the beginning, OCE for M4 will be due for next week, Tuesday. I have to change the calendar to make that happen yet. The P&L for M5, let's talk about that a little bit right now so that we can get into N5 here, to M5. We have talked so far about models that are all linear. Why are they called linear? Okay, increases at a steady rate. That's what makes it linear, but why is it called linear? You're making this too hard on yourself. If you look at it, what's it look like? Well, if you look at the graph, it's just a line or a series of lines, right? So it's called a linear model because of the way it appears on the graph. So we're going to start looking now here in our second part of class at models that do not form lines on the graph. And one such example is when we start dealing with interest. So what I want to look at is two situations. In situation one, or situation A we'll call it, you start out with $10,000. And you are going to add $200 each year for 20 years. Situation B, you start out with the same $10,000, but you are going to add, I'm making this one up, 1.75% each year for 20 years. Now, as I look at these, which one looks to be a better deal at first? Well, to figure out which one's a better deal, what would I have to know about situation B here? Perfect. So I would take 10,000 times, so that's $175. So that 1.75% each year looks like it's only $175. So what one looks to be a better deal at first? A does, because you're getting $200 a year. Let's go to a spreadsheet here. So that's our year, and we're going to look at the balance. We started out with 1,000, but we got or 10,000, but we got $200 at the end of the year. So we ended year one with $10,400. At the end of 20 years, we had $14,000. Simple enough, right? Are those numbers big enough you can see them? There. So at the end of 20 years, we ended up with $14,000. Perfect. Let's do this again for the 1.75%. So if I start out with 10,000 here, how would I started out with 10,000 at the beginning of the first year. I could find that 1.75%, but rather than finding it like I did here, I just found the $175. What if I want to find the ending total? Well, to find the ending balance, I would have to take the 10,000 plus that $175, right? Which is $10,175. The 175 represented the interest. The 10,000 was the beginning balance. The 10,175 is the ending balance. We know that the interest was 1.75%. The beginning balance is the basis of that calculation. That's 100%. So the ending balance would be 100 plus 1.75, which is 101.75%. Any questions on where the 101.75 came from? It's just the full amount plus 1.75%. So if I had taken that $10,000 times What's 101.75 as a decimal? Careful. Perfect. And if I multiplied 10,000 by that, I'd get $10,175. That's my ending balance. So that's what I'm going to do here. So equals 10,000 times 1.0175. I get that amount. That was each year for 20 years. Yep. The whole 20 years? Nope, that's each year. So you can see in the second year, if it was just $175, it would have been $10,350. But why is this number larger than $10,350? Yeah, they got interest on that first $175 again, didn't they? So at the end of 20 years, they're going to be greater than what we had on the linear model. So this is not linear. Here in this type of model, the next number is we're adding or subtracting a piece of the previous balance. Talking about $10,000 get you a little excited? Actually, I'm not a broke college kid. I've been out of college for for 21 years now, and $10,000 gets me excited too, so don't feel bad. Yeah. I have several friends. I got lucky with college, but I had several friends that walked out of college with between $60,000 and $70,000 in student loans. Yeah. Well, that's that motivation to get good grades and get scholarships, right? Okay. So what I'm going to have you guys do is I'm going to have you guys jump over to M5. And I want you to look at that problem situation 1. Now, we didn't have time to do the P&L, so I just give you this example to work on. I'm going to have you read that problem situation 1, kind of talks about, actually, we can't get away with that, can we? Because it is referring back to the P&L questions. Let's go through these together then for the first question, and then we'll turn you loose to work after that. Okay, so it's talking about how the quantities change over time, and it wants us to look back at the P&L questions. So in P&L question 2, population of a small town in Ohio was 5,500 people in the year 2000. Census data showed the population decreased by approximately 2.5% every year. So let's go back to that interest example I used. So this is back to the example I just made up. We had the $10,000. What did we multiply it by each year to get the next year's balance? We multiplied by, am I? Okay. So let's take a look back at that interest example I just did. We started out with $10,000, and then how did I find the balance? What did I multiply by to find the balance at the end of the first year? It was 1.75%. But what did we adjust that to? Yeah, 1.0175, right? That was the 1.75 added to 100% to get 101.75%. So each year we multiplied by that. And how many times did we have to multiply by that? 20 times. In math, do we have a mechanism for multiplying by the same number repeatedly? Yeah. There you go. Perfect. So if I take my 10,000 times 1.0175 to the power of 20, I get that $10,147.78 that we got in our spreadsheet. So now it's referring back to PNL2. And what PNL2 was, is it is a town that starts with, in the year 2000, the population is 5,500 people. But rather than increasing, the population now decreases by 2.5% every year. So up here, we took 100 and we added the 1.75. What do you think we're going to do down here? There you go. 100% subtracting 2.5% is 97.5%. So to get the population at the end of the first year, what would we multiply by? To change 97.5% into a decimal, it is perfect. So that'd be at the end of the first year. If I wanted to represent in year 2010, how many years would that be? 10 years. So this would be to the power of 10. So what we've done here is we've created a model where the population, I don't know why I put 2,000 there. That shouldn't be 2,000, should it? What should that be? The starting population. So we've created a model here where we represent the population of this city as 5,500 times 0.975 to the power of x, where x is the number of years after 2000. So what we found here is this takes on a form. This is a starting value, just like the y-intercept or the starting value in our linear model, only in the linear model we added or subtracted from that value. Here we are multiplying that value by a change factor. So it's a starting value times some sort of a percent to the power of our years after that starting value is measured. So the variable here is time from the starting value. Okay. So what I want to do is, if you look at number 2 here, there's a little bit of reading there in question number 1 where they talk about what this is. This is called an exponential model. And it's called an exponential model because the amount of increase or decrease is not the same every period of time or for every piece on our independent axis. It's exponential because the change depends on the current value. So it's a piece or a percent of it usually. We could use a ratio. It could be, the ending value is 16/15ths of the starting value, but typically we express it as a percent. The first example we did with the interest, we had 100% plus that interest rate. So that meant we had a value that was bigger than 1, right? Larger than 100%, or 1 is a decimal. That's referred to as exponential growth. If you were to take like a business math course or something like that, they would talk a lot about compound interest and exponential growth. And it's tremendous how money can grow over time if you start when you're young. The second example we had, the population of the town. There you go. Those Gerber Life Plans are a great example. You start out when a kid is born with just a small investment. It's unreal how much it grows to. Now, in the second example, we had the city population, and it was decreasing. So in that example, it was 100% minus the percent that it was decreasing, which gave us something smaller than 100%, or 1. And that is referred to as exponential decay. So, the next part of the exercise, I want you to just talk about what type of examples you can think of that would have exponential growth and exponential decay. We're running a little short on time, so I'm going to rush this a little bit. We're going to jump up to number 3. Number 3, suppose that the cost of attending a certain 4-year private college, here's our cost of tuition and student loans again, right, is $16,500 in 1977, and that cost increases 3.2% every year. I want you to create, so this is for number 3, create the algebraic model, create the equation. So to create this model, I'm going to use 2 variables. C is the cost of tuition in the current year, and T is the number of years after 1977. So cost is equal to, what is that initial value or starting value? 16,500, good. Now if you use different letters, that doesn't matter. Since this is an exponential model, it's going to be multiplied by something. Now they gave a number of 3.2%. Are we going to take 100% plus 3.2 or minus 3.2 in this example? Is the tuition going up or down? It's going up. So it's 103.2%. So what goes in here in our model? Perfect. To the power of t, the number of years after 1977. So what I want you to do that is part B. So for number 3B, find the values for 1987, 1997, and 2012. And I want you to sketch a graph quick. So I'll give you a couple of minutes to do that. Just for the sake of time, we're going to put these points right on the graph. So in 1977, I could have made that my axis here. I'm going to do that, in fact. In 1977, well, excuse me, what was the cost? $16,500, right? So for 1987, our model, 16,500 times 1.032 to the power of t was the cost. For 1987, what number do we put in there for t? 10, perfect. So we get a cost of, ooh, I didn't do that right. I got an extra zero in there. 22,608.98. For 97, what did we put in there for t? So 16,500 times 1.032 to the power of 20. 30,979.75. Now, just looking at these first two values, the horizontal change is the same, isn't it? It's 10 years. What's the vertical change? Well, from here to here, the vertical change, if I subtract, I get 6,108. Here, if I subtract those two, I'll let you guys punch that in the calculator. What do you get when you subtract those two? Perfect. So you notice that change is increasing. So if I were to sketch this curve in here, it's not a straight line, it's curving up. Okay, well, we're almost out of time. We got 3 minutes till we're going to get cut off here. So what I want you guys to do is I want you guys for next Monday, work through on your own the rest of M5. See if you can come up with the doubling stuff, and we'll start talking about M5 on Monday. We'll finish talking about N5 on Monday. And then do the PNL for M6. I will put an announcement on Blackboard, and I will send it out to your emails. It'll probably come out to your Nicolay emails, trying to straighten out the grading and the assignments. But for right now, due for this Friday, which would be 10/27, I'm going to have you do the M3 out of class exercises. The P&L for M6, I'll have that done for class on Monday. I'll have it due for Tuesday. Now, you guys said some of you are completing it on the Carnegie website, and you said some of you are scanning it and sending it in. Okay. Well, if you're going to scan it and email it in, I'll have you scan it and you can email it to todd.hoff@witc.edu. Or you can do it from Blackboard. Blackboard, you can go into communications and email instructor, and that'll send it to my Nicolay email. I'll get it either way. Okay, well, with that then, we'll get cut off here in about 20 seconds, so we'll see you guys on Monday. I will also have this recording posted on Blackboard, by the way. I'll let you know in that email I send you, I'll tell you where it's posted.